before. Oh well, first matter, I can tell you another story. No, from a mysterious place.
He's got a better one than you. This one is better.
Right, okay, let's make sure that I'm serious. I want to start looking at something which one normally would not associate these two things together. One is algebra and the other is differential equations. Now, particularly, I'm only going to talk about ordinary differential equations just to keep the thing moderately simple. But it also works for partial differential equations, and there are many applications. Now, the whole problem with applied mathematics, from my perspective, is that you have a model of some situation. It could be physical, could be social, could be economic, whatever. And it reduces to things changing. So you have rates of change, which means derivatives, you have to collect them somewhere, and you end up with a differential equation or a system of differential equations to solve. The question is, how do you solve them? And if you look at the history of differential equations, you'll see that people have been working at different methods for different types of equations for several hundred years. And it's still an ongoing process. Whether it will ever stop with the ultimate is a mystery, an unknown at the moment. So if you take a differential equation, how are you going to solve it? Well, you can start off with a nice easy one. Now, as usual, of course, the prime represents differentiation with respect to the independent variable, which of course will be x, because you all remember that x is the unknown. How do we solve this? Well, it's quite simple. We integrate it. We get a constant. So we integrate again. And there we are. If we know the answer, we can go on to the next problem. What happens now if you get something more complicated? Let's take, right, I'll change variable now. So the x double up plus omega squared x is equal to 0. Well, we all know the solution to that because we did elementary trigonometry, and we know that it would be x of t would be easy peasy. It is easy. However, what happens if you have a slightly more complicated problem? Related to this, no. Okay. That equation arises when you're analyzing the motion of a charged particle in a time-dependent electromagnetic field. That's where the modern application was. It actually is a very old problem. It goes back over 100 years. It was what you might call a toy problem. You know what the toy problem is? You know? Well, then why wasn't you asking? You are expected to ask questions. Think of this poor audience here, not me. who don't have the same facility for asking. So,
Well, actually, they do. They can ask questions if they wanted to.
oh,
But
Is there anyone there we can say hello to them?
absolutely, yeah. We have quite a number of participants.
Ask them to say hello.
The thing is that they're
They are
in a mode where they can't speak, unfortunately.
But we say hello to them, they can chat in the chat.
Yeah,
Is that right?
we already did that. Yeah.
And they did say that we have a proof of life.
Yes,
We do.
yes.
Because Peter would appreciate that there are people
that was
listening
the
to.
proof of life.
Yeah. No, a proof of life of the audience.
Oh, I thought you were talking about me. Well, I could do with that. Now, there's a horrible little white thing. That's better. Now, there was a question which I now can't remember.
What's toy model?
So,
Toy problem? Toy model.
ah, toy mold, yes. Well, it's one that you make up. You may have a particular physical situation which is quite complicated to model, but you look at the essentials of it and you just say, well, let's make up an example, physical thing, which could be used to model this problem. Now, a very simple one, in fact, it was the original one, it was the original problem before they did all this complicated stuff, was to get a retort stand with arm and put a string through it with a little bob at the bottom and tighten the thing up. Right? Usual sort of thing. You're familiar with that? You did first grade chemistry? You didn't. Well, kindergarten chemistry did. Now, you set the pendulum going. And you know all about it because some centuries ago, Galileo observed that it was isochronous. Yes?
Period is independent of where you let it go.
Essentially. That's not completely true.
I know, but it's true to first approximation.
Oh, it's actually a very good approximation, provided the angular displacement is not great. And then it's a very good approximation because you can approximate it with this equation. And as you say, it's isochronous. We do know what isochronous means, don't we?
No, we don't.
Same prono time, same time.
I thought we had
Same
to do-
time if you drop it from here or from here.
Right? All you have to do is have a working knowledge of Greek. Well, you do, don't you?
To some extent.
Well, that's a working knowledge is to some extent. Now, but then the problem happens that you don't tighten it up properly. And what happens if you don't tighten something up properly? It starts to slip. And if it slips, it gets longer and longer. And right, but you're letting it slip down. Oh, right, very good. Doing some strange things.
Like a repeated problem.
Yes, that's the ultimate end of it, of course. But, so, because the omega squared is actually related to the constants in the problem, which is the strength of the gravitational field and the length of the string. If the string is slipping, it changes in time. That then becomes a very interesting problem. It's an interesting problem because it's difficult to solve. They're the best sort of problems, as you well know. Now, was around about 1880, when this experiment was done, and someone looked at it, very, very smart guy by the name of Lorentz, and he said, oh, well, if this is slowly varying, we have an adiabatic invariant. Right, now, you're allowed to say it.
It's an adiabatic invariance.
Yeah, well, don't be that embarrassed. You're actually doing the work of 4 people.
Very true.
No, actually 5, sorry. Now, adiabatic means it's not really constant, but because everything in this time frame is slowly varying, it's roughly constant. Now, but this was one thing, and as I say, it was a long time ago, and not really what you might call of any relevance. Why would it be of no relevance? You call the lab technician in and you get him to screw the thing up. Honestly. Don't you ever do any laboratory work? No, just say no.
Can a paper be a laboratory?
Paper be a laboratory. Well, it can be if you want to burn a few houses out. It's very good experimental work. And the thing about it is, it usually guarantees you a nice, comfortable home. It's pretty about the iron bars, but apart from that.
The thing is, Peter, it's not exactly that problem that you're describing, because if the clamp is loose, if the clamp is loose like this, then the rate at which the length is changing is dependent on the force that's being applied at the clamp point. And that force is part of the dynamics of the system. Whereas when you just have omega of t, as in your problem, you are externally specifying omega of t. So it's not an internal dynamical variable. So that's where there's like a machine that's actually changing the length as an explicit function of time. And it's not the dynamics of the system that's changing the length. So it's a slightly different problem to the one you're saying.
Why not? No, if you just put the thing in there, have the thing tightened so it's just not moving instead of going,
Yes,
then you just loosen it a bit.
yes.
Won't it be the dynamics which will be lengthening the string?
But in this differential equation, when you have an omega of t is a specified function. It could be like
Oh,
t
who
squared,
said?
right?
Who said it was a specified function?
Well, that's the way that you write down. You said omega of t, which means it's a given function. It's not determined by the dynamics of the system.
No, it depends upon the dynamics of the system, right?
Yeah, so then it's a different differential equation from the one you wrote down. That's all I'm saying.
It's different than this one.
And to the bottom one, because the bottom one is where you have a prescribed omega of t, prescribed from the beginning by a machine that's going to
It
actually
doesn't
set.
have to be described.
It has to be, because you've said it that way, omega of t. So you've said it. So
Well,
it's an
it varies
explicit
in
function.
time.
Yeah, but so in other words, that differential equation, you have to be given omega of t in the beginning.
Oh, I've never been given it. I just solved the problem. Sure.
In terms of omega.
Oh,
Is a
no, I
solution.
wouldn't do that if I were you.
Maybe I'm happy with, maybe I'm happy. Well, I'll wait a bit. Let me wait and see how things develop.
Okay,
Yeah.
right. Now, as I said, the problem here is to solve this equation. And as I said, 140 years ago, Lorentz came up with an adiabatic invariant. Now, so, oh, well, that's nice. Then in the 50s, this last century, 1950 time, The same problem was encountered with particle accelerators. You know all about particle accelerators? Oh, good. You can take over the next part of the description in that case. To my understanding, and I am quite prepared to be corrected, you have a particle supposed to be going around in a more or less circular orbit, and it's being accelerated because there's an electromagnetic field there which is rapidly varying. Is that close enough? Oh, good. And so you end up with that, and the problem is how to solve it. Right. Well, that's a serious problem. Well, I've already told you, of course, how you solve it, which we did that on Monday, I think. Monday. Yes. And so I'm really going to sort of move around the solution to look at another part of the problem. And that really gets us back to our initial equation, y double prime equals 0. Can you use transformations that leaves that equation invariant? Right, so you do an x and a y thing, and we get the same equation. How would you do it? Well, there are two ways you can go about it. One would be finite transformation. Now, there's a problem with finite transformations. They sort of keep on keeping on. If you use infinitesimal transformations, you can just stop at the first infinitesimal. You don't have to worry about infinitesimal squared because it's infinitesimal. It's infinitesimal compared to the infinitesimal. Okay?
I
So,
understand. Sorry, I don't quite understand what is an infinitesimal transformation.
right. Well, that is a good question. We'll have an x and a y. And we're going to transform them, so we'll put bars on top. And that will be equal to the original x and the original y plus an epsilon c and an epsilon theta. And epsilon is infinitesimal.
Okay.
Okay? It's cool now. Does anyone catch though? Oh, what's the catch? You're very good at answering these questions.
What's psi and eta? Are they like?
Oh, they're functions to be determined. Yes, no, that's true. But what I want to point out is this is x, y, right? That equation has y double prime. So we need not only the changes in x and y, but also in the primes. So we have to do an x. So I think, way over there. Oh, this funny. Looks like the I saw a cat chasing the other day. Right. But the prime here, of course, is the prime, the differentiation with respect to x bar. So that would be the x bar, the y bar. That's the x plus epsilon c over
Isn't it the
Yeah,
other
I
way
think
around?
something's wrong, isn't it? Can we just sort of do a little bit of arranging? I think we better do a bit more arranging. Right, so better? Okay. Now, we should expand that. So we'll do something which is a bit terrible, but this is applied mathematics. And that will be then we do the triple there.
Yeah.
All those terms that we're not going to take any notice of.
Well, it's plus and it's minus.
What's wrong?
Oh, no,
Yeah,
it's
good,
fine.
that's right.
Look, I must apologise for this
Yeah,
terrible
I
board,
figured that out.
but I'm a little bit out of practice.
No, you are too advanced.
Sorry.
You're too advanced.
Now that will be y dx minus epsilon and then plus and all the other terms of epsilon squared and worse, so we don't worry about that. Right. So let's just summarize that.
It makes some. I'm not sure what the price is.
Something doesn't seem right there. So dy by dx seems like it should have
Which term are we looking at?
that one.
This one?
Yeah. That's
dy by dx times xi dx.
okay, agreed. Yeah, okay, that is right.
But what I'm not sure about is this term.
You take the inverse.
We tail expanding one,
Yes,
tail.
tail expanding 1 over 1 plus epsilon.
So let's just put it back into prime form. We have y bar prime, which equals y prime plus epsilon into beta prime minus y prime prime. We forget about the yes. Oh, sorry.
No worries.
Chasing me. Oh, I should have gone to that top one, you mean? Oh, I'll go to the top one. I must say, it's very nice balls.
Thank you.
Thanks to Bruce.
They are very nice.
Thank you.
The baby could will
Yeah.
lift them up.
Yeah.
Right, so I'll just summarize that a little bit. Y bar prime y prime plus epsilon. What is it? E prime. All right, now. So that means e prime minus y prime has zero. Now, that's not all, of course, is it? Because we're dealing with the second derivative.
Why do we want y bar prime to be the same as y prime?
Sorry?
Why do we want y bar prime to be the same as y prime?
Why? Because we want the transformation to leave everything invariant.
Okay.
Right? So it has to be the same.
Okay.
Now, how would we go for the second derivative? Come on, I'm waiting for some assistance.
Well, we do the same thing that we did before, now to the y bar prime.
Okay,
So we need,
Isn't it easier now?
all right, so
Probably a similar thing, we have to do the epsilons again.
Because it's over dx bar, right? Sure.
so we need x bar prime.
No, x bar prime, the prime means derivative.
oh, wait a minute, that's not right.
Oh,
Isn't
yes,
that
oh,
x
yeah,
bar?
oh, yeah, it's x bar, just x bar.
In this approximation,
Yes,
about
yes. You disregard that. That's where we say that the infinitesimal square.
Okay.
Mathematically take the perception of this.
Right, well, we should actually replace this here by y prime plus epsilon and
So
So when you calculate a derivative, dy by dx is the limit as epsilon goes to 0 of y at x plus epsilon minus y of x over epsilon. And we're doing a similar thing here. Like we are calculating y bar prime minus y bar, minus y prime over epsilon. And that's going to pick out the difference too. Okay. It's like we changing the system directly by small amounts.
so now eventually we can take the derivative. So I suppose I can go down here. Right. I think, well, perhaps we don't want the epsilon in there. So you want you to double prime. A big problem with my arithmetic. What's the problem with the arithmetic? I'm sorry.
Why have you got a 2 y prime? So when you say what?
Another y prime factor.
Just tell me where.
I'm not sure.
Oh, good. It was still here, huh?
I'm not sure it is.
Not sure there's one.
We did a product rule. What happens is that we had to differentiate, we had to differentiate that guy.
Differentiate
Yeah.
Y double prime side prime, Y prime side double prime.
Yeah.
Okay.
That's all right.
Yeah, it looks right.
That's not.
It's not. Oh, because y prime doesn't multiply c prime twice. So going to the last line doesn't look right.
Yeah, there's something wrong there.
Isn't this wrong here? Because how did you go from here to here?
Because that's what I wanted.
Oh, these two, they do give you this, eh? So I don't
No,
see, it doesn't, because that's got a double prime there, you see.
yeah, that's the. Oh,
So these terms are all different.
well, they shouldn't be.
Okay, so let's figure it out.
That's what I've asked you to do.
Okay, so we're getting there, we're getting there. Okay, so did we make a mistake over there?
No, that's right.
Okay,
Then we can look at the Taylor. Is it correct?
so that when I do the Taylor, 1/1 plus epsilon gives you 1 minus epsilon times c prime. So yeah, he's done it in one step, but
Oh, sorry. I wish you could put the correct head in there.
okay, so it's dy prime by dx. Epsilon eta double prime minus y double prime c prime minus y prime c double prime. And then I have to multiply by the tail expansion of this, which is going to be 1 minus epsilon c prime plus higher order terms of epsilon.
Oh.
And then we get dy prime by dx here. If we get epsilon term, we get this multiplied by 1, which is this here. Sorry, so I get this whole thing, eta double prime minus y double prime c prime minus y prime c
So
double prime.
it's epsilon prime times dy prime over dx, which will give you y double prime instead of y prime.
Say again.
If we multiply epsilon c prime with minus sign, you multiply that with dy prime over dx, right?
You've got neither, so.
Yeah, you got.
When you multiply out,
There you go.
Yeah.
don't you want that term to multiply with dy prime over dx as well?
So we're gonna, so let's do it. So again, dy prime by dx plus epsilon. So the first one, we are gonna get epsilon is this times this. That's what you're saying.
Yeah,
So that's dy prime, let's call it y double prime, right?
that's right.
Y double prime c prime, and it comes with a minus sign.
So here we have y prime instead of y double.
Ah, good, you found it.
Thank you.
Not near,
Is this
just one prime, isn't it?
one prime's enough? So we've discovered the error.
Didn't
Yes,
go.
no, you've done it very well.
So, and then I've got to get this times this, right? So I get plus eta double prime minus y double prime c prime minus y prime c double prime.
Which
And what
is
did he-
precisely what we want.
What did we have here? Eta double prime
Well, actually. let me just,
minus y double prime c prime
uh,
minus y prime c double prime minus c prime y prime.
What have we got? Have we got the primes in the wrong place?
Let's call this one. One.
Okay.
This term two.
All right.
Two. Eta prime three. Three. Minus y double prime c prime.
So what the prime there?
Yeah, so that's what I was trying to find out earlier. Yeah, but in your formula there, you have two y prime. Should it be y double prime though? In the next line.
Okay, so now we've corrected that error. Now let's go down to here.
Or something else, okay.
Okay,
Well,
So
two there, okay.
That will be y prime and the other one will be y double prime.
okay, here we go.
Okay. So it's not what we want. Right, and there you are. Eventually, you get there. Now, you can extend this to higher derivatives. But the wise person would just look up a book or a paper which actually writes down the general formula. And an even wise person wouldn't even do that, because they know that there's a program which does it for you. Right. Now, so the basic part of this is, if you have a second order equation, well, first order equations aren't too interesting. You have a second order equation, which are the ones which tend to occupy our attention. You want to find out what functions eta, you see, satisfy that equation. Of course, where you put the y double prime, you put the equation, and then that will enable you to solve the problem. However, what's the catch? There's a catch.
So hold on, we have to say, we wanted this to be the same as y double prime, right? So
So we want that
Yeah,
to zero,
yeah,
right?
good.
And
So we've got two equations so far, the previous equation and this equation.
yes, but one's really a consequence of the other. So,
Which one is a consequence of which?
well, the second one would be a consequence of
The
the third.
first. So that's nice. So we don't even need the second one.
Huh?
So we don't even need the second one.
Oh. Bad news for you, my friend. Now, what sort of transformations would you like to use? Oh, come on.
Well, I'd like to use invertible transformations.
Oh, great. They probably would be useful, but I was actually thinking at the sort of the lower level, with not so many syllables.
Linear.
Well, look, let's make a compromise. How about point? Now, what's a point transformation? Takes a point, right? We're dealing with xy for now. So you have a point xy, we go to a point x bar y bar. Right? No derivatives. The point transformation is just with the two variables. Okay. Right, now I'm going to run into some technical problems here. So point transformations makes life a lot simpler, because you don't have to worry about higher derivatives. So what do you do now?
Substitute in the
Right.
space.
So you substitute now what we have. Oh, ether, okay. So today to ether x squared plus 2y prime to ether. I think there must be another one. Does that seem reasonable? No, sorry.
Y double prime is naught. Why can't we use that?
Huh?
Y double prime was naught, right?
Well, we're doing it as a general thing, and then we'll substitute the differential equation. Your point is quite solid. Right, so we've got that. Then we've got minus y prime. Then to, or the, to see. What's the We want all of that to be zero.
So I don't understand what happened now.
Oh,
How
well,
do we get that first thing?
Hoping it is, with probably great difficulty. Right, we want that thing to be zero. So I'm making C and eta functions of x and
I
y.
see,
So I'm just expanding the
I
derivative.
see, I see. Thinking of y as a function of x. So when I differentiate with respect to x, I have to differentiate, partially differentiate with respect to x and with respect to y, and then multiply with the derivative of y is equal to x.
Precisely. Yes. Now, as you pointed out, we have a piece of useful information. Now, don't mumble. I'm deaf.
Why double prime is zero?
Right. You didn't even have to put a question mark after it. But that's the differential equation we're dealing with. So we're going to substitute the differential equation. And when we do that, let's try to see. Okay, so we'll get y prime. Oh dear. Can I just replace the y double prime equals zero in this? Is that okay for you? No. But it's sort of. Oh, really? And so that gets rid of all of that. And that. And that. So we achieve a simplification. Right. What next? No, it's just a simple equation to solve. It is simple. It's the simplest equation you can get at second order. Well, let's see now. Now, why can I do that?
Some kind of reverse product rule, maybe?
No.
No.
It's a polynomial.
Sorry?
It has the form of a polynomial, then the coefficients have to be zero.
Right, the statement is. C and eta are functions of x and y. The y primes are explicit. So, y prime cubed is different to y prime squared, it's different to y prime, it's different to y prime to nothing. See? So we take y prime cubed, and we get something. That would be zero. Y prime squared. from the requirements. Okay. Oh, that's sorry, this is you. And it's just. I really must apologize for this absolutely frightful writing. I hope you can make some sense of it. I'm not used to writing. I'm not. I'm actually not even very good at typing anymore because I just talk to the machine. Okay, so we have 4 partial differential equations, which we can solve without any difficulty whatsoever. First one, C is equal to A of x plus B of x times y. And then we'll get A to beta ay squared will be 2b prime. So beta will be C of x plus D of x y plus B prime y squared. Well, so far so good. Now we have some conditions. We differentiate with respect to x and y. D prime plus 2 D double prime y minus A double prime minus B double prime y is 0. And what we conclude from that? B double prime is 0 and D prime 2D prime, sorry, minus A double prime is 0. And then we go on to the last one, which is what was it? C double prime plus E double prime y plus D prime y squared is 0. What does that help then? C double prime is equal to 0.
The transformation.
C double prime is equal to 0. C triple prime is equal to 0. Right. Now, I think this funny looking how did I do it? Oh, and then of course you have the A double prime. Okay, now we won't go through the actual calculation because it just gets a bit too boring for words, and I think you've been bored for words long enough. How many solutions have you there?
I know the answer because Osana has been working on this problem with Sue and I believe there's going to be a 3-parameter family solutions.
No, it won't be a
Okay.
solution. Yeah, try 5.
5, yeah.
It's an 8 parameter,
8 parameters.
right? Oh, sorry. 8 parameters. I think you can work that out if you do something. 2, 4, 7, and 1 there, you make 8. And when you write them all down, you get an 8 parameter solution. And each one of those solutions, of course, is a solution. That means you can write down 8. This is where we really run out, don't we?
Well, we're reaching the end of the lecture now, so it's a good thing that we run out.
I was just going to give you what I call the bottom line.
There's an 8-dimensional Lie algebra.
Sorry?
There's an 8-dimensional Lie algebra.
Yes,
Which one is it?
it's SL3R, of course.
SL3R.
Yeah.
Very nice.
Well, that's the bottom line, isn't
Write it down. That's very elegant.
it? Okay.
Yeah, that's right. Yeah, that's right.
So when you do when you can use it's taught to know when one is an extension of the other when it comes back to that sequence. So I think that's one. I don't think it's some sort of extension. I think it can be written as an extension. Okay. Yeah. Right.
That related torsion theory of knobs. That's the way it can be written. Every group can be written as the extension of the pair of number. The generalized torsion theory that you compose it to 2 parts. Fitting into extension.
I don't know about the torsion tree, but I was just taking a group and then if it was simple, then there was no norms. But if there was a normal subgroup, then I could always write it as an extension. That's what I'm saying. Then I didn't know about that.
Right, well, that's-
I just wanted to know if it's.
The end of the thing. But do you know what the Lie bracket is?
I do, but I'm not sure if everybody does.
You don't, so you're honest. That's the Lie bracket. What's another name for a Lie bracket?
Commutator.
Thank you. Yes. Yeah, that makes it simple, doesn't it? Right. So you have the. Sorry, no, sorry, I'll just stick that. You take the Lie bracket with all of these things. You know into fun doing it, and it gives you the algebra SL3R, and that is the Lie algebra of the equation y double prime equals 0, which is, of course, is just one out of an infinite number of equations? Close enough to infinite? Yes, right. So the question then is, do you have to sit down and do this for every second order equation? It takes time, as you may have noticed. It's also it could be, when you think of some differential equations, it could be quite a messy calculation. And so we need some general results to save a lot of effort. Now, I won't tell you what the answer is yet, but the other thing, of course, is that you may have a particular differential equation for which you need to find the symmetries for a reason which will become evident in our next meeting. And so you have to do the calculation. And some of these second order equations can be quite nasty. You believe me on that? Right, good. And if they're nasty, one has to do something about it. And what's the ideal thing to do? Well, actually, you get someone else to look after the problem for you. There's a chap at the CSIRO in Melbourne. You know, heard of Melbourne? You're not sure.
In Australia?
Sorry?
In Australia.
Yes, that's right. It's a famous place. Well, lots of famous people were born there. And he invented a program to do this. And that program has been around for well over 50 years, I suppose. Now, what's the problem with a program of some 50 years old?
Doesn't run anymore on modern computers.
That's a pretty good. It's because people keep changing the software. Not so much the hardware, I think it's the software. But it used to run, I think it was in reduce. You've heard of reduce? Oh, okay, well, it's not bad. You must be older than you look.
I've heard it from Sibu actually. We had a Lee Symmetry conference last year, and that's where I learned about it.
Ah, see, you know everything.
No, I'm still learning.
Anyway, it's a very good program, very robust program. There have been some attempts by others. Oh, it's the Canadian guy. Oh, I've forgotten his name now. He and one of his students wrote one, and it had feet of clay, which means
Very easy to break.
no, it doesn't give you the right results. Just trying to think who the guy was now. Is it British Columbia? No, I can't remember. Anyway, it's no good. It fails. I had the sad duty to point this out to him with well-hidden glee. Anyway, it can be done on a program, and in fact, these days, it's incorporated into Mathematica. I don't know if it's the same program. I think it is actually. But it's all those fun things you can do with Mathematica, and it just makes everything so much easier. So I'm sure that must be at least time and a half.
Yes, that's
Tuesday. Yes. You know, if you were polite, you would say, please, sir, may I leave the
Yeah.
All right.
Lisa, may I?
Oh, yes, no, just as if we don't get knocked over in the rough. The next exciting event is next week, is it?
Yes.
Oh, all right.
Perhaps we still give opportunity to ask questions, those who don't have to leave immediately. If
Oh,
that's
yes.
fine.
That's true.
If there are any questions online, please let us know.
Oh, yes, I forgot about people online.
Yes, Johnny, we'll contact you by email. Actually, the presentation will be published on the YouTube channel of NITheCS, so you can check out the YouTube channel in a couple of days, and you will see the video there.
Well,
So there was just a request for the video, otherwise there doesn't seem to be any questions.
oh, all right. Well, in that case, let the stampede begin.
Thank you very much, Professor Leach. Thank you for the attendees, and we look forward to resume next week.
Right.